bonds. And in principle, there are three types of bonds that we worry about: covalent, ionic, and metallic. And each one has its own characteristics that can distinguish it so that we can separate the types that we're talking about. First off, a little review. Ions, atoms that have lost or gained electrons. Electrons in the outermost shell. We're always going to be talking in this unit about the valence electrons. And of course, the noble gases don't make ions because their shells are already full. However, the point really of this whole unit is everybody else, which does not have full shells already, wants to be like the noble gases and do something to have full shells. And so that's where these bonding and compounds will come in. Of course, we have two types of ions. We have the positive ions called cations that have lost valence electrons. These are the metals. And a couple examples with Na+, Fe2+, and aluminum 3+. Please note the positive exponent showing you that it's a positive ion and how many valence electrons they have lost. And then there are anions. The negative ones have gained valence electrons. These are usually the non-metals. And so examples are phosphorus 3-, oxygen 2-, and chlorine -. And again, the exponent, negative for gaining valence electrons, the number telling you how many they have gained. So you can tell right off the bat here that it'll be really important to distinguish the metals and the non-metals. And in fact, we already did this picture in our last unit. Here is the three main groups across the periodic table. The easiest way to keep track is remember where the semi-metals are, basically along the staircase. And then everything to the right is a non-metal. Everything to the left is a metal. Though sometimes boron, a semi-metal, can act as either a metal or a non-metal. So having this in general will be important for this unit. Which are metals, which are non-metals. We also have our trends that'll be very useful for this unit. Our ion charges, +1 for any element in column 1, +2 for anybody in column 2, an alkali earth metal. We skip the transition metals, and then we get to the last 6 columns, +3, ±4, -3, -2, -1 for the halogens, and 0 for the noble gases, which don't make ions. And then, of course, those have to match with the valence electrons. That trend you also see. Everybody in column 1, the alkali metals, all have 1 valence electron, 1 electron in their outermost shell. And then 2, skip, 3, 4, 5, 6, 7, and 8. We, of course, skip the transition metals because they have no simple pattern. However, we will be able to determine what charge a transition metal element will have based on what it's bonding with, because it turns out everybody wants to be like a noble gas. The noble gases have no charge, don't make ions. Well, once you have a compound and things have come together to be like the noble gases, the compound will also have no charge. And indirectly, that'll allow us to figure out what the transition metal in the compound must have been so that the overall compound has no charge. Now, if you remember from Bohr's model, the electrons in the atom have energy, and we can divide that energy up for every single electron based first on what's called a principal energy level. That principal energy level matches the row the element is in. So if you're in row 1, period 1 shell, you also have 1 principal energy level. And then if you're in row 2, it's period 2, you have a second principal energy level. You also have sublevels. So the principal energy level is actually split into different sublevels. What that means is the electrons for that element may have energy that fits into one or the other sublevel. If you have 3 principal energy level, then period 3, you then have 3 sublevels, and once you get to the 4th row, you then have 4 sublevels. The sublevels are named S, P, D, and F. These stand for sharp, principal, diffuse, and fundamental. These are from historical spectral line descriptions. If you remember when we were doing our spectrum lab and looking at the different elements in the gas tubes, and you could see different colored lines. Some of the lines were narrow or thin, some were a little bit broader, some very sharp, some kind of fuzzy. That's where these 4 names are coming from. It is important, however, to remember that electrons don't really move in specified orbits, say the way the planets go around the sun. They are found in regions of space. So while the energy levels is very important from Bohr's model, he thought that they were in circular orbits, and it turns out that they are more in regions of space, and these regions are called orbitals. The S energy sublevel contains 1 orbital. There are 3 orbitals in the P sublevel, 5 orbitals in the D sublevel, and 7 orbitals in the F sublevel. Each orbital can hold at most a maximum of 2 electrons. And I'm going to jump ahead a slide to this one here. This is how you could, if you wanted, sort of block out the periodic table in terms of sublevel energies. In other words, the energies the electrons have in the different sublevels. And so here we have the S sublevel, and we have 2 columns over on the left side of the periodic table. Remember, an orbital can have only 2, so just 2 columns in any one row here for the S sublevel. We have the P sublevel, which can have 3 orbitals, 3 times 2, giving us 6 electrons. And over here we have 6 columns that are what we would call P-type electrons. The transition metals with 10 columns, 10 divided by 2, 5 orbitals. And so it takes 10 transition metal elements is going all the way across to fill up a D sublevel. And then the 2 portions of rows 6 and 7 that we pull out, they are the F sublevel, and it takes 14 to fill that up, 7 orbitals, 14 electrons. Here is how it looks in terms of energy. In other words, when we're talking about the first principal energy level, this would be for the electrons for hydrogen and helium, row 1. They have the least amount of energy. And then as we progress down the periodic table, so down any particular row, the amount of energy actually increases. So electrons that are in outer shells for the 2nd, 3rd, or 4th shell have more energy than they do in the first shell. And so this diagram is done in terms of increasing energy. And then as you can see, when we get to what would be row 2, that principal energy level splits into 2 groups. We have the S sublevel and then the 3 p orbitals that represent those energies. And then when we get to row 3, we now have 3 of them, S, P, and D. And then if we kept going, we would bring in the Fs. Now, interestingly, okay, you'll notice that right here there is an overlap, that the 3D actually has a little bit more energy than the 4s electrons. Well, where do the 3D start? They start in row 4 after calcium, in other words, after the two 4s electrons, we then bring in those 3d electrons, and that's why they don't appear until then. They actually have a little bit more energy than those two 4s. And so there's a little bit of overlap, and that's partially related to why we call them transition metals. It's literally a transition between the S and the P type energies. Over on the right here, what you see is called electron notation. It's a way of distinguishing the energies of every electron that the atom contains. So for instance, down here at the bottom, and I've done this in reverse order, so the lowest energies are down here at the bottom. Hydrogen only has one, so it's a 1s1. Basically, the 1 is the principal first row, the s is the sublevel, and then there's only one electron in that s orbital. And then we get to helium, which of course has 2 electrons in that one. And then we just build our way up. Notice that the s's never get more than 2. The p's go all the way up to 6, because we have 6 columns. Again, there are 6 columns over there for the P group or the P block. And, you know, as we move across, we are filling that block up. And so boron has 1 P electron, carbon 2, nitrogen 3, oxygen 4 P electrons. The halogens will always have 5. And then the noble gas has 6. And in fact, the ones I haven't read here, which are the noble gases, every energy level, every sublevel is completely full. And so that's one way that you can distinguish them from all the rest. These are what are called electron notation. You did have some assignments that you did a few weeks back where you looked at the pattern for doing what's called electron notation. You can see how much they have in common from one element to the next. And then what we're basically worried about are those valence electrons that we're adding on the outside. And of course, you can group them. As I mentioned, the electrons don't really belong in orbits. They're in regions of space. And as a result, the different orbitals have shapes to them. The s orbitals are basically spherical. A sphere. So for a 1s electron, it can be anywhere in a basically region of space that's a sphere. When I get to adding a second or third shell, now those electrons are at a greater distance from the nucleus, but they still basically could be anywhere within a spherical shell from that nucleus. Pretty simple for that one. Little bit more complicated when I get to the p orbitals. These have what are called a dumbbell shape or figure 8 shape. So the electrons can be somewhere in this region of space or somewhere in that region of space, possibly even going back and forth between the two, depending on how many electrons they are, up to a maximum of 2 in any region of space. And then as we move across the P elements, we just change the orientation to take care of all 6 possible spots, 3 orbitals, but 6 areas of space that the electrons can fill. The d orbitals have what are called a cloverleaf shape or 4-leaf clover kind of look to them. And so again, this is a region of space in which one electron may be in any of these 4 regions. And of course, it's moving all the time back and forth between these things and interacting with electrons that are in the other orbitals, because of course, electrons repel each other. They never want to be together if they can help it. Now, once we get past the d orbitals, gets kind of complicated because of all the electron-electron interactions. So here is some modeling of what the f orbitals would look like and a picture of theoretically what a g orbital would look like. A g orbital would be a sublevel for something in row 5 or 6 or 7, which an electron can get excited to be in. In other words, get extra energy to excite it up to a higher energy level. But in generally, we're going to be dealing with the S, P, and D types for the most part. So let's talk about chemical bonds and using these valence electrons. Compounds. 2 or more atoms rearrange their valence electrons to join together. So this whole unit is all about what's happening to the valence electrons. We're not worried so much about what's happening to the inner shells, just the valence electrons. Now, an atom becomes stable energy-wise when that outer shell is totally full or it's empty. And then something that we're going to be doing a lot is paying attention to the octet rule. And the octet rule is the outermost full shell contains 8 valence electrons. Those 8 valence electrons are basically separated into 4 pairs. One of those pairs is the s orbital, and the other 3 pairs represent the p orbitals. And so we've got a picture of neon, a noble gas, its second shell completely full, and we have represented those 4 orbitals by one of them being an S and then the other 3 Ps. Each one has a pair, maximum of 2 electrons in it. Now, this is a representation that's sort of on the page 2D wise. In reality, this is a 3D region of space, so you can't really use this picture exactly the way things are, but it does help us kind of see where the different areas are. Don't forget, of course, that hydrogen and helium are a little bit different because one shell, only one orbital, just one s orbital for them. Okay, we're going to start off with metallic bonds. Metallic bonds are between 2 metal atoms. And the valence electrons are shared in what we call a sea of electrons. Way to visualize this is think you have a box or a jar of marbles and they're surrounded by water. In other words, inside the box or inside the jar are marbles with water. Now the marbles are packed and so they don't move, but the water is free to move in between the marbles. So if you were to tip the jar or box around, the water could slosh through. Well, they represent the sea of electrons. Those electrons are free to move all through the metal, whereas all of the metal atoms, which no longer have their valence electrons, and so are called kernels, all these positive ions, they're kind of all locked into place to represent the metal. The electrons are free to move about. This is, in fact, why metals conduct electricity so well. They literally have electrons that are free to move. And so electricity is simply a flow of electrons in one particular direction, whereas if you did not, say, have it connected to a current, the electrons are kind of randomly moving all over the place. So 2 important ideas. Metallic bonds are always between 2 metals, and their valence electrons are shared in a sea of electrons. Covalent bonds. These are between 2 nonmetals. Their valence electrons are also shared, but they are shared in pairs. And those pairs are between the 2 atoms. So here we have 2 carbon atoms. Carbon, 4 valence electrons. Would need 4 more to get to that octet of 8 to be full. So what happens here is this carbon is bonded 4 times to one other carbon and to 3 other hydrogens. But in so doing, it basically locks 2 electrons in a single bond between here the carbon and the hydrogen. They're not free to move all over the place. They covalent bonded molecules will not conduct electricity well. Their electrons aren't free to move. But each of these hydrogens thinks it's got 2 valence electrons. That one shell is full. And each of these carbons is surrounded by 8 valence electrons. So as far as the carbon is concerned, even though it's sharing one with the other atoms, it's surrounded by 8. It has its octet. Its second shell is full. So electron pairs are simultaneously shared between atoms. And we could have single, sharing 2, double, sharing 4, or even triple, sharing 6 valence electrons in covalent bonds. So literally, we could have 6 all in one region of space between 2 atoms, a very, very strong bond. So why is H2O H2O? Well, if you think about an oxygen atom for a moment, it has 6 valence electrons. Again, we're only worried about the valence electrons. To get to 8 means it needs 2 more. Hydrogen, on the other hand, has 1. It needs 1 more for it to become full. So by rearranging those valence electrons from the hydrogens with the 6 that oxygen already had, and it's always in this kind of bent shape, by the way, we end up with 8 around the oxygen. It thinks its second shell is full. 2 around each of the hydrogens. They think their one shell is full. Everybody is now, quote, like a noble gas. Everybody is full. They are being simultaneously shared between the 2 atoms. Everybody like a noble gas. And overall, neutral, no charge. Now, as I mentioned, we can have single, double, and triple bonds. And H2O showed us some single bonds. Well, here's another single bond. This is F2, a fluorine molecule, one of the diatomics. There are 7 of them. You can always remember them by the gens, as in hydrogen, nitrogen, oxygen, and the halogens. Those are the only ones that will be with a 2 here. It has a single bond. We had 1 fluorine, valence number 7. Another, also with its 7 valence electrons. They are sharing a pair there in the middle. So each fluorine thinks it has 8, 2 shared, 6 unshared, a total of 14 valence electrons needed to complete this molecule. Here is a diagram of an O2 molecule with a double bond. 4 electrons shared between the 2 oxygen atoms, and then each atom has 4 that are not shared. However, when we count this one up, 2, 4, 6, 8, 10, 12, we only get to 12 total valence electrons. So it only took 12, 2 less than the 14 that the single bond particular molecule took, and you will find that that pattern is true. Going to doubles, we do not need quite as many electrons overall to fill out the compound. However, it's the same idea. This oxygen right here has 8 valence electrons. It has the 6 it started with plus the 2 that it's sharing with that oxygen atom. It also has 8, the 6 it had, and the 2 it's sharing. And then an example of a triple bond with 6 valence electrons in between the 2 nitrogen atoms for N2, and then a pair that are not being shared. Notice only 10 total valence electrons. So 4 less than what the single bonded had to form this triple bond. This is a very strong bond. Most of our atmosphere is nitrogen, and in fact, it takes the energy of, say, a bolt of lightning to break this bond so that it can be transformed into other material that we can then take in through our diet to get nitrogen into our bodies, an important nutrient. So single, sharing 2, double, sharing 4, triple, sharing 6 valence electrons. And finally, we're going to talk about ionic bonds between metals and nonmetals. So just to repeat, hey, first one, metallic, 2 metals, covalent, 2 nonmetals, and now ionic, metals and nonmetals. The valence electrons here are not shared. They are lost or gained. They are given or taken. So one atom gets the valence electrons, the other one loses them. They become ions. The metals, positive ions. The nonmetals, negative ions. And as ions with positive and negative charges, they attract each other just the way magnets would. And they form ionic crystals, such as NaCl, table salt. They will have this kind of crystal pattern to them where you see positive, negative, positive, negative, positive, negative charges throughout the crystal, all locked in place. And please note, not just in 2 dimensions that you see on the screen here, but in 3 out of the screen as well. As I said, the cations, metals that lose their electrons, their valence electrons, and become positive ions, and the nonmetals that tend to gain electrons and become negative ions are called anions. If I take salt and put it in water, stir it up so it dissolves, literally speaking, in the dissolving, the positive and negative ions will separate in the water, float around as ions, and conduct electricity quite well. On the other hand, if I go back to the covalent bonds, which are between nonmetals, sugar is a good example of a covalent bonded compound, a molecular compound. You dissolve that in water, that will not conduct electricity the same way because they do not break apart into ions. Their sharing kind of locks those in place. So it's very important to get that different bonding, different things are going on with those valence electrons. So here's a picture of an ionic compound called calcium phosphide, and you can see all the electrons, not just the valence ones, but all of them. But honestly, that's kind of hard to look at all of them. So we're just going to pay attention to the valence ones. So just to see the difference, that's all of them. Calcium in row 4 has 20 of them, so 4 shells. Phosphorus in row 3 has 15, so it's in 3 shells. But we're just going to pay attention to the valence electrons. Now, calcium has 2 to give away. Phosphorus has 3 it needs to become full. The thing is, the 2 calcium electrons given to the phosphorus, well, the calcium will be emptied out, but the phosphorus won't quite be complete yet. So you have to have a combination of calcium ions and phosphorus ions that will, in fact, equal out. In other words, every valence electron has to go somewhere so that the calciums are all empty, but the phosphorus are all full. Well, between 3 and 2, think of 6, I need 3 calcium atoms, each one losing 2 valence electrons. I need 2 phosphorus atoms, which would then need 6 total for each one to become full. Those 6 valence electrons that the calcium's lost split apart to each go 3 to a different phosphorus atom. But as you can see now, each phosphorus atom is full. 2, 4, 6, 8. 2, 4, 6, 8. Its outer shell is full. The calcium's 4th shell is now empty, but of course its 3rd shell is still full. So the last outer shell is full in both cases. So we have our calcium 2+ ions. We have our phosphorus 3- ions, but together they produce calcium phosphide. And notice that the subscripts here, 3, 1, 2, 3, and 2, 2 phosphorus. Why are they the 3 and 2? Well, because of how many I need so that the transfer of valence electrons from the positive metal to the negative non-metal ions exactly matches. Can't have any left over, and you can't be short any. All right, quick kind of pop quiz. All you got to tell me is metallic, covalent, ionic. And seriously, folks, that's what some questions on the next quiz or test would be. You'd be given a compound and asked, is this metallic, covalent, or ionic? So what do we got to pay attention to? Metallic, 2 metals. Covalent, 2 nonmetals. Ionic, 1 of each. So what do you think for copper and aluminum? Metallic, correct. All right. KF, potassium and fluorine. Ionic, that's right. Potassium, K, column 1, an alkali metal. F, fluorine, a halogen, a nonmetal. So it is ionic. All right. C3H8, covalent, carbon and hydrogen, both nonmetals. That is correct. Okay, PCl5. Okay, if you call it metallic, then they both have to be metals. Okay, is Cl a metal? No, Cl is a halogen. It's a nonmetal. Phosphorus is a nonmetal. This is covalent. All right, little trickier here. KCN, there are 2 bonds. What are the 2 bonds? One between the K and C and one between the C and N. A bond is always going to be between 2 atoms and only 2 atoms. So what do you think? Ionic and covalent. Between the K and C, that is ionic. K, again, potassium, that's a metal, alkali metal. C, carbon, is a nonmetal. Nitrogen, also a nonmetal, so it has to be a covalent bond between those. All right, last one, what do you think? I heard covalent. Can anybody tell me why this won't happen? Yes, Ni is a noble gas. Noble gases don't make ions, number 1. Number 2, they're called noble gases because their shells are already full. They do not react with other elements. They don't form compounds. So you do have to be careful, folks, and pay attention to not just the fact it may be a nonmetal, but which nonmetal is it? The noble gases will not be part of your compounds. To summarize, this is literally like 6 questions on a test. In other words, the answer being metallic, covalent, or ionic, knowing, hey, is it 2 metals? Is it 2 nonmetals? Is it 1 metal and 1 nonmetal? You might be told similar to the way we were done on that previous slide. In other words, you're actually given a compound or you're given 2 elements, or you might just be told, they're 2 metals. What kind of bond? It'll be metallic. Notice, by the way, we didn't really spend a lot of time on the metallic bonds, and we won't. Most of our energies will be spent on the covalent and ionic, and we're going to start off mostly on the ionic and then end with the covalent. We also have to worry about valence electrons. Okay, metallic, valence electrons that are shared in that sea of electron. They don't belong to any one atom. Covalent, which form molecular compounds, are shared in pairs. Could be single, double, or triple, but still shared in pairs, kind of locked in place. Don't really conduct electricity well. And then ionic compounds form ions. The electrons are given and taken. We have positive ions. They've been given away. The valence electrons have been given away. And we have negative ions, the nonmetals that have accepted or taken those valence electrons. So just knowing this gets you a long way to being able to do this unit. Because really what we're going to be doing is looking at all kinds of combinations of these situations. Okay, so that ends our Notes?